that kind of, we talk a lot about at this summit, the serendipity of bringing together different people, very technical people, entrepreneurs, investors, researchers. And what I love talking about serendipity is we met first in 2012 at a random dinner of a friend of ours, Andrew Cohen. I don't know if you recall that. He might be here. I don't know if he's here or not. And then a year or so ago, introduced by another mutual friend, Jeremiah, who's speaking later today. And that's the way the world works. You mentioned you were working with Jeremiah in the past. Where was that?
Jeremiah and I worked at OpenWave back right around the time it just merged from phone.com. So right at the first attempt at building out the mobile internet. And we did not make a fortune there.
Well, maybe the next one will be.
So you
learned a lot. What was the biggest thing you learned about? Aside from, don't talk about him, because we'll talk about him later.
Management matters.
Management matters?
Yeah.
And is that something, we're skipping around a little bit, but while we're on that topic, management matters. So in regards to that, what did you learn that you're integrating into your new company?
From OpenWave, I'm not quite sure. That was a difficult experience because I had my own company called Avogadro, which I started with a bunch of ex-Microsoft folks, the kind of core of the Internet Explorer team at Microsoft. Left to go start a company called Avogadro. We did that for several years and sold it to OpenWave, and then I took on a job. I ended up being the CTO there. The only thing I learned from that is that I never wanted to be in a business that sold anything to handset manufacturers or carriers, because it is impossible to break through and get margin in any way unless you're Apple, and Apple did it in a profound way by completely turning that the sort of economic model of the carriers upside down. But for everybody else, it was just fighting for crumbs.
Yeah,
and it was impossible.
Well, I mean, that's an important learning. We all go through frequently it takes a couple attempts at different companies to get to the one that really takes off. But we're stepping ahead. I want to start back in the early days. So you founded a company 19 years old. What was that?
Oh, Lord. I founded a company, I was a co-founder in it, called Propellerhead Software down in North Carolina. It was just a little 5-person group that we probably sold 6 months after we created it. And we worked on networking software. I didn't go to college when I was a kid, so I just started, writing code when I was
What was the computer back then, that first computer you were using?
I'm weirdly old school. It wasn't a PC. I grew up writing software on DEC machines, on a PDP 1134 and on a VAX back in the day. But I grew up in that hacker culture around MIT, which I still think is the kind of the greatest period of software development and software creation to date.
Why is that?
In that one little place. Well, because, what was called LCS, the Lab for Computer Science, was sort of ground zero beside Berkeley, beside Stanford, but really it was LCS, ground zero for the software revolution. And it was a thrill to just be around there and around these, young thinkers, and I was 12, 13 years old hanging out with these guys learning how to code.
How'd you get into that at 12, 13? I mean, how did you, the parents were went to work and you went to hang out with them?
Yeah,
nice.
Just like that. Hacking and trying to iterate on.
What was the biggest kind of revelation at that stage? This is for me, and aside from the brilliant people that you're hanging out with, can you recall back to is there a nugget that sticks with you for this drive to hack and create?
The thing that still sticks with me and that still matters is how important play is to learning.
Right, sure.
And everything we did as young hackers back then, and again, this is the old school hacking, not contemporary Russian hackers trying to break into things, but
give us an example.
Hacking. Well, we wrote games. And that's what we did. We wrote games, and if we broke onto a machine, it was because we needed, time sharing. We needed more time on a mainframe somewhere, so we would break in, and that's where we would host some of our Star Trek games, that kind of thing. But what was at the heart of it was play. Every day was play, and that was something that I try to bring into my work life today.
So then you skip ahead a little bit. We'll do a little short bit on, you were at Microsoft for a little bit in the Internet Explorer.
A little bit, 10 years.
10 years. Well, let's say a little bit. Well, in the big picture, that's a little bit.
It was a big part of my life, yeah.
All right, so what was the biggest learning there?
There's so many things to learn from that.
You were the
Maybe
first one on the Internet
biggest-
Explorer team.
I started the IE project at Microsoft. Of course, that grew to be 300 people by the time we really built something that exceeded what Netscape had, because they were crushing us. Netscape, the browser that they had was so much better than what we were doing for.
So stand of hands, like who's old enough or young and why, who was around during the first browser war, Netscape IE? Okay,
Right.
Good portion. So we know kind of
I
what
have
this
just one
is.
thing to say. You're welcome, and I'm sorry.
It was a mess. When we got to late IE3 and then IE4, we were doing extraordinary work. The big lesson I got out of Microsoft was talent matters. And Bill just had this very deep philosophy that you do whatever it takes to attract the best engineering talent. And that is sort of his entire day was organized. Like that's the first priority. And then the very last priority, the 19th priority was like meet with the CFO and talk about money. It was just about talent and getting people aligned onto projects. There's some downside lessons, which is, don't flip off the government. Negotiate. I think Qualcomm and others and Apple and others, Facebook, et cetera, can learn from what happened to Microsoft in the late 90s. We got just crushed by the DOJ, and that utterly transformed the culture for the negative. I'm not somebody who believes that what happened after that moment opened up this great new technology spring that allowed for Google and Facebook, et cetera, to come alive. I thought those companies were already doing their transformative work, whether or not Microsoft hadn't been, as I said, crushed by the DOJ. But the problem was internally, it really put Microsoft on its heels, and it became a relatively toxic place for quite a while, and not that kind of place I had joined that was just absolutely revolutionary. Like when I got there in 1990, 91, it was revolutionary. Like that was the spirit. And it also felt like if you were a serious software person, it was the place to be. It's hard to imagine that there was a period of time where we were pulling like the best people out of Apple day after day after day. Now, no chance that would be happening. But that's what it was like in the mid-90s there.
And you were there for a little while, so 10 years, and through the DOJ challenges, among others. And then all of a sudden, you wanted to get a Ph.D. in neuroscience.
I got tired of tech. I got tired of the web.
You got tired of tech and tired of the web. You got tired of the thing you created.
I didn't create it. Tim Berners-Lee created it. I exploited it, as did Netscape. I just wasn't interested in where the web was going as just as a computer science, architectural problem. It was just fundamentally uninteresting to me. It felt like, I always say, frankly, the average PhD thesis these days. It's like the transferal of bones from one grave to another. That the web architecture was like, let's redo all the windowing architecture that we built in for Windows or built in for Mac OS or X and translate it online. So nothing was fundamentally new. It was just a translation of legacy technology. All the Doug Engelbart inventions of the early 70s were just getting retranslated to the web, but we weren't doing anything new. Now, of course, if you're a business person or a financial engineer, the web, was the most dramatic transformation of probably in 100 years. But from a computer science perspective, it just was boring to me. It just felt like it was all just going to end up being sports and porn. And what am I supposed to do as a technologist to innovate here? I'm uninterested. So I left all of that in 2003 and sat around thinking about what to do next and started taking classes at Columbia in New York. And weirdly, one thing led to another. I started a job. Basically, I was disemployed for a long time and started a job working in a neuroscience lab, doing really software, looking at experimental data. And then that one thing led to another, and then I joined a Ph.D. program and spent over 12 years either as a bench neuroscientist, really getting my hands dirty, running experiments or analyzing data, and then ultimately spinning out in 2015 to start the company I'm running today, which I started with several other neuroscientists from Columbia. But I found my passion there, and a passion that I don't think I ever really fully had when I was just writing software.
Did you think, were you going in to say, hey, this is just, I want to explore mentally new things, and eventually this will end up into the next startup? Or just you wanted to inspire yourself?
I wanted to first...
It wasn't like the step to get there. Was it that programmatic in your mind, or was it I got to get out of this and just knew something new and who knows what's going to happen?
So the first thing is I needed to deprogram. So I don't know if this is the right path for everybody, but I highly recommend at least considering it, which is when you hit that burnout point, as I did in 2003, I just did the opposite of what I was doing. So I came to New York, started at Columbia, and actually went and got a degree in classics, in Greek and Latin. And it was a blast, but it actually gave me 3 years to really disengage from tech. I lost contact with even Jeremiah over here. And really give myself a chance to reset so that when I did start learning about neuroscience and taking it kind of seriously as a career, I didn't start out thinking, oh, how am I going to marry this to my software background? I just said, I want to be a neuroscientist. I love, and this is something I'll talk about as we
sure.
Go forward in the conversation, which is they were just the most interesting people to me. And it just comes back to this rule I've tried to hold myself to now for 20 years, which is to focus on who before what. Decide who you want to work with, and then find out what within that you want to work on.
Which is also ties back to what you were saying before, management and people. It's all about people and everything that we do.
Yeah.
People build businesses, people build tech, people make money, people hire other people. And it's not the business that does all that.
Yeah.
And I think we get that lost frequently about when people talk about startups and or about businesses. It's not the business that's the most important thing. It's the people and what they do for other people.
Yeah. Ultimately, I would hope that more technology companies were created by humanists. And again, what I loved about the neuroscience community at Columbia that I joined is that I found a bunch of scientists who were humanists. And they were really in it for questions about humans and about their own humanity.
When you started getting into that, though, when they said, okay, this guy comes from 10 years at Microsoft, do we really want to hang out with this guy? I mean, there's positives and negatives from Microsoft and kind of a mantra, which is probably different than most neuroscientists, but I'm just guessing.
Oh, they were fine. No one got mad at me. Once I showed them Linux running on my laptop, they all forgave me. That was an easy thing for me. Like I said, at Hacker in the early 80s, I was there at the dawn of the BSD revolution.
Are many neuroscientists hackers as well? Or probably
So
a
neuroscience
type of
as a field really splits between the biological, and there's even a fork of that, which is just human psychology, what we'll call cognitive neuroscience. But there's a lot of people like me who did work down at the level of individual neurons and trying to understand the physics of neurons. But then there's this whole other huge branch called computational neuroscience, which most of you now know as machine learning. But computational neuroscience, for instance, Columbia and UCL, University College London, have really the world's great computational neuroscience center called the Gatsby Center. DeepMind, Google's DeepMind, spun out of the London side of that. You can say in some ways, CTRL-labs, my company, spun out of the Columbia side of that. But we are at heart machine learning folks who are interested in machine learning as it intersects with biology, with real neurons. And what can we learn from real neurons to apply to and create new machine learning techniques, and vice versa? What can machine learning results give us as, what can they teach us that allows us to form new, at least hypotheses about how real neurons work? And that, that's a problem I'm happily engaged on for the rest of my life until I die. So I have no next career after this. This is the one. I found the mother of all machine learning problems, which is decoding the human brain. And there's no reason to think that we're going to do that for centuries to come, or finally solve it. So this is what I get to work on for a long time.
So that in the lab or with the colleagues when you're working on the Ph.D., was there an aha moment, or was there a trajectory where obviously you just shared the goal, but what was the aha moment? Is okay, now this is potentially a business, or do we want to make a business out of it? What was that kind of behind the scenes? Because there's a lot of researchers and technical folks in school or that have left that when do we commercialize what we're working on? Do we want to? Is it the right thing? Or,
so I was at I was a hacker within neuroscience. So I did real biology in neuroscience. I created viruses, neurotropic viruses, in particular rabies. And oddly enough, I'm one of the world's experts on rabies because I made a lot of it. And it became a really an interesting tool in experimental neuroscience because we use it to manipulate neurons and to trace out circuits, because rabies is this virus that crosses synapses between neurons. So you can use it to kind of exquisitely interrogate a neural circuit. My first passion was to say, like, how can I find a way to like commercialize all this interesting engineering we've done to rabies? And I really kind of like hacked on the virus. And I unfortunately couldn't find anybody else to do that with me. What I could find is my co-founder, Patrick Kaifosh, who's really an absolutely brilliant neuroscience, machine learning thinker. And as we started to talk through, like, what are the other tools that are available from experimental neuroscience that haven't been exploited commercially? And that was the key idea. It was almost like Genentech in 1975 when they launched, this era of the biotech revolution, with the first synthetic protein ever created in the whole proteomics revolution. Starts with Genentech, but they were harvesting 30 plus years of bench science that had been done that hadn't been commercially exploited. And we started to think about, well, neuroscience has a ton of these tools. For us, it was things like spike sorting. I won't explain what that is. That just hadn't really been commercially exploited. And we thought, like, what would you do if you could spike sort in real time? What kinds of things would you exploit with it? And that's kind of what led us to the company. It wasn't necessarily a goal of creating the world's first real day-to-day brain-machine interface, but rather, what can we exploit? What's been done in the lab that we can exploit? And most of that was because I just wanted to work with Patrick, and I wanted to work with other people like Patrick. So I wanted to create an opportunity to work with people like that rather than try to fight it out in academia for grants. I would fight it out for VC funding instead.
Is it an easier fight?
No.
Just a different. How would you explain the difference of that fight?
Harder to get money out of VCs, but more faith when you do. And for the kind of work we're doing, and maybe for many of you starting companies out there, for Jeremiah, you need high faith investors, ones that will also help you raise more money. But if you're working on the crazy deep problems, the really hard problems, you need people who aren't just looking for tilting up the website in 6 weeks and getting ARPU up, within 6 months, but instead they're going to think about scientific metrics and technical metrics and other metrics that will ultimately lead to revenue and profit, but that they can track for the 3 to 5 years it might take to build the thing that can be transformative. And that requires high faith investors and high IQ investors.
Agree. And so the perfect timing. So let's talk. So what is CTRL-labs? And then we're going to show a couple of videos in a second. But give I'd actually say the layperson for everybody, and then a more technical kind of response of what you would say to other neuroscientists.
To other neuroscientists or entrepreneurs?
First, the entrepreneurs.
Okay. So CTRL-labs is a neurotechnology company. We are building, I think, a pretty extraordinary set of technologies that allow any human to start to control a machine, whether that's a laptop or their phone or an avatar in virtual reality or a crazy 7 degree of freedom robotic arm, but any complex machine by using their motor neurons, the neurons that represent the output of the brain. You can call that a brain-machine interface. We prefer to call it a neural interface. And this is the device that actually does that. This is a device that does differential surface electromyography. I'll take it off here. And it allows for a bunch of channels of EMG that are the electrical activity of my muscle. What we're able to do is look at the electrical activity of the muscle and create a map of that back to the actual electrical activity, those zeros and ones, if you will, of the neurons in your spinal cord. Those are the final output of your brain. So we are building this brain-machine interface that extends your nervous system out to the world of machines. It's a science fiction idea people have been talking about since probably, I don't know, the 1930s. But we're doing it, and it's real. And
So
it's
why
not a
now?
headset.
So why now?
Because we can. We had a big insight. I did my Ph.D. really in motor neuroscience. I did much work with viruses, but my questions were around how does the brain form a set of signals that allow you to do this crazy stuff you do, in particular with your hands. Just to ground you all, this is the most skillful part of you. There's probably twice as much nerve going to your hands. Technically, it goes to your arm. Your hand's kind of dumb. I call it a meat mitten. It's, the arm actually controls the hand. Twice as much nerve controlling all this as even your mouth, the chewing and speaking muscles. And then everything else is kind of dumb. Your feet are really dumb. All the skill is here. And it's pretty extraordinary what you do with this. You basically do everything with this. You might ambulate with your legs, but again, that's a low skill action. Compared to this, which is incredibly high skill. I always try to make this reference to what I'm doing right now, which is taking a sip of water, which really wasn't cognitively difficult at all. That is the hardest thing I've ever done in my life. There's nothing that compares to the difficulty of that task. Not speech, not math, not listening. That was extraordinarily difficult. The degrees of freedom that have to be modulated, the fact that the weight is shifting in here, the fact that each time I pick it up and put it down, it's a different bottle because I sipped something out of it. It has a different texture on the outside. All of that I have to adapt to in real time. This incredible movement computer up here is sending out all these commands and taking back in information to allow you to do that skillfully. That skilled reach and grasp that we talk about within motor neuroscience is what we're tapping into with our device. And rather than doing this outrageously complicated thing of taking a sip of water, watch a robot try to do this, you'll laugh. Watch a cat try to do it and you'll laugh. This is us. This is what we do extraordinarily well. We want to allow you to do that now to machines with the same kind of devil-may-care cognitive load, just absolute fluidity of control over machines. And we'll show you some examples of it.
Cool. Let's see if it goes when we're ready. They will help us in the back. It's also there in front of you if you want.
Oh, I'd rather look there.
I have to use the right button, sorry.
All right, so this is somebody.
Oh, it's me.
What we did was we started out by trying to say, like, this is an older device you see on my arm. This is the new one that we're about to
I think
start
I had
sampling.
one even older than that about a year ago. There was wires everywhere.
Oh, God, they were horrible back then.
It was great.
A lot of progress. So what's happening here is we built up a model, a computational model that's reading out the electrical activity of my motor nerve and basically trying to virtually recreate my hand. All the fine postures, the continuous postures, not just is my hand open and closed, but sort of what it's doing. And of course, there's no camera here. There's no Kinect that can see my hand. This is just built up from the nerve. And of course, that's all that's needed, because that's what causes the muscles to move and contract. What you'll notice here is it's the nerve. So if I send the signal to open my hand, the virtual hand opens and closes, and I can do that for any kind of control. As long as this nerve is doing it, it doesn't matter if the hand actually moves. So we started with that. Oh, no, stop there. We'll get to that in a second. We started there because we said, if you can virtually recreate what the hand is doing, then I don't need all those devices that you normally control. I don't need to move the mouse or bang on the keyboard or all those slow things that you do. You said, why now? I can flip it around and say that we have all of these new experiences, these new computing experiences coming online. They kind of started with the iPhone in 2007, and now there are more immersive ones coming in VR and AR, et cetera, that are all getting data to us in new ways, but none of them are trying to get data out of us in a new way. And in a lot of ways, they're making us dumber. And I've said this phrase many times, that these devices, these experiences are mocking us.
Yeah.
Because they're mocking our bodies.
It's one of my favorite statements that you make, just because everybody tries to make people smarter, but a lot of the things these days as technology is doing the opposite.
I think humans have outrageous, as I tried to show with that example of taking a sip of water, you have outrageous cognitive capacity. You take in phenomenal amounts of information, visual information, auditory information, et cetera, proprioceptive information, outrageous amounts. But getting data out of you is really hard. Your muscles that ultimately take all of that nerve signal, your muscles are slow and very, what we say, low dimensional. They don't really do that much. They're so slow. So we go through this goofy, mechanical process of interacting with the machine. But your brain can do orders of magnitude more than that, way more than that, and way faster. So that's what we're trying to do. Let's get right to the nerve and ignore the muscles and stop making you have to do the monkey dance to interact with the machine, and instead have your brain interact with machines directly. Why don't you show this next video? Because I said, once we can do that, we can get rid of all those old devices. Here's how far we can go with it now. Now, here's my co-founder, Patrick. What you're seeing is he's playing Asteroids, which is a game that would be hard to play on a phone moving it around. I don't know what you would do. Here, he's not moving at all because he's trained himself to do 2.5 degrees of freedom, like a joystick, and he's able to actually fly around, control the, do the thrust and rotate it and fire, all without moving at all, just out of the nerve signal. Of course, we can scale that up now. Imagine if you were controlling 5 ships in Asteroid all at the same time. You simply can't do that with your hands, but you can do it with your brain.
I think there was one more.
Okay, open the hand.
Oh, this is awesome. So this is Greg Wayne, a friend of ours from DeepMind, who's actually on our board. And Greg is trying the hand for the first time, and he's just figuring it out. And he's just getting control of a single finger, and he's like, okay, I think I got it, it's right, it's kind of cool. But the cool part of this is Greg never had a hand. He was born without one. And it took him less than 2 minutes. And again, he didn't lose a hand, he never had one, or never had most of the hand, certainly not the fingers. So he actually was able to get control of this virtual hand really in about 2 minutes. And he learned it in real time, a hand that he's never had before. And he's doing a grasp. He says at the time, he's saying like, I've never grabbed something in my life. Like, he's grasping and generating. You see that little grasp meter going up and down, which is the amount of force. That's embedded in the nerve signal, and he figures out how to control that. And it's not like he goes through, physical therapy for a year to do that, to control a prosthetic. This was 2 minutes, direct from the nerve. I love that video because it just gets across the fact that you have all this control built into you. It's not in your hand, it's in your brain.
So these are fascinating. Obviously, I think everybody's in awe and silent regarding that. The pieces of the puzzle that, obviously, as a visual tech event, and then when we met, we wanted to invest, but it is not much visual tech, and it was later stage. But we want you to succeed and everybody else to succeed, whether or not we invest. The question is, there's a little bit of visualization now, and is there, kind of visual tech aspects in the future, or it doesn't even need to have any visual tech aspects in the future? Just share a little that you can. And then let's dig into actually building the business and what are the challenges regarding that.
So we have a weird relationship with visual technology, with CV. On the one hand, we compete with it. Like, I'm trying to make the Kinect and those kinds of technologies irrelevant. Why would I use a camera looking at you to know what you're doing when I can just instrument you and get to the real ground truth, what your brain is trying to do? So I don't want to see your hand. I want to listen to the nerve that's trying to control your hand.
Makes sense.
So in that sense, there's been a massive investment in the kind of AR, VR world around CV as a means of tracking your body. And again, I said, doing the monkey dance as a means of interaction. I think that's a silly way of interacting in these new immersive environments. I want to have kind of magical powers that go way beyond what my body can do. As one of our scientific advisors says, he wants to have a tail. And I want to go far beyond having a tail, but that's the experience I want in VR or AR. On the other hand, we're very reliant on CV for how we do our training. So to be able to build up these models of how the nervous system controls the body and then exceed them, we need a machine learning ground truth and a baseline. And that we very much rely on really the most sophisticated CV work being done anywhere, most of which we brought in. It's not stuff that we've created. So thank goodness that has been, a pure point of deep innovation for the last 10 plus years. And then I'd say, even beyond that, really the biggest advances in machine learning that have impacted machine learning everywhere really started with the revolution in the attack on ImageNet and in particular the 2011 and 12 results that Google got to. And those results, that marriage of deep nets with conv nets, have had a profound impact on all of us doing, what I'll call deep ML work. And whether you call that CV or not, it comes out of the world of CV and what that world was trying to push forward rapidly.
And that will continue in your mind within Control Labs of being, one part of it will continue for a long time, or at some point in regards to your goals, you won't need it anymore. I mean, it seems like there will be constant tuning.
This is an argument within the company. I'm very strident, and I say it's not relevant to our future. It was irrelevant to building up to where we are. Okay. My co-founder violently disagrees with me.
There must be entertaining discussions.
Yeah, well, we're a healthy culture, and fortunately we don't quit over these things.
Good. So what's the biggest thing you learned when you started, since when you, let's say, gave it a name, we're going to do this, and so in the last, what is it, about 3 or 4 years, 3 years now?
3 years.
3 years, right? So what was the biggest surprise from that 3 years ago to today that you've gone through?
The biggest surprise, which we didn't show in any of those demos, is that we could get to single neurons. So we had a thesis about this that was just kind of born out of, I wouldn't call it even experimental neuroscience. It had never been done before. The idea that I could, via a non-invasive device, get to sufficient signal noise that I could actually see electrically the activity of a single neuron in the spine, and that I could see the activity of hundreds or thousands and algorithmically separate them, what we call spike sorting. We knew on first principles it was possible. I'm stunned at how fast we got to that result. And that's a big, big result. We are the first place in the world where you can reliably look at individual neurons from outside the body. That's not been done before. You used to, you stab into things or you drill into the skull to go look at a single neuron. So now we're saying, why would you drill into the skull to look at a single neuron? I can do it without drilling.
I like your approach much better. I don't really want any holes in my head. I mean, on purpose at least.
The hardest part, the downside part was that we tried to create a software company thinking that there would be lots of devices out there and we'd just go get them off the shelf. That turned out to be totally untrue, and we had to make a very expensive investment and fundraising around designing hardware. I still wish we were a software-only company, but I think when you're doing really vanguard technology, you just have to kind of solve the full stack problem.
Yeah, if you're pushing the envelope and the rest of the pieces don't exist, you have to build them.
Yeah.
What's the, so you've been through up and down roller coaster of different companies. And there's a lot of people in the audience that are trying to build companies and have succeeded and failed. I've succeeded and failed in different companies. What's the biggest mistake you've done in the last 3 years at Control Labs, and what have you learned from it?
Biggest mistake. Oh boy, there's like a mistake every day.
Or choose one that is the most, it doesn't have to be the biggest on a metric level, just.
I mean, this is almost trite, but I know anybody who started a company or built something bigger regrets this. It's sort of when you know that something's not working with somebody, waiting too long to address it, whether that's actually asking somebody to leave or just really changing their role. So, just waiting too long to make personnel adjustments.
And how do you measure that? Because I agree with you. What is too long is the biggest challenge, because everybody wants to keep trying, everyone wants to do something else.
Everyone says that, but
right? I mean, I don't think there's one answer. But what is your gut? Like, is there a trick that you've learned or taught yourself to say, it's now too long already?
I've taught myself to listen to my partners in the company. That's what I've taught myself to, because I think I'm probably the most hopeful person, the biggest optimist out of the set of founders. And the others are maybe a bit more realistic, and I'm always hopeful that this is going to turn around with this person, or maybe if we nudge in this direction, it'll work out better. And I should trust my partners a bit more on their desire to no, let's move on and optimize for the group overall.
Right. I've got more questions. We're almost out of time, but we have time for questions from the audience. We've got mics. There's a hand over here for one. Who's on that side to the right? Keep your hand up so they can see you. Over there, Dan, to your right. Yeah, there you go. Right there, right behind. Yeah, there you go.
So first of all, thanks for the conversation. That was just flat out awe-inspiring.
Great.
So I was very interested that you said the really tough thing is getting the data out, getting new data out from the body.
Yeah.
And you talked about the hardware side, but it sounds as if you're still using basically one mode of getting out that data. Have you explored the possibility of multiple diverse sensors or of other ways of getting down, getting that data out? Since that seems to be the bottleneck in some ways.
Give us a context of what your day gig is, just for everybody.
I lead a research team in radiology at NYU School of Medicine, and one of the things we're trying to do is start instrumenting our scanners to give us as much multifaceted information about the body as we can get.
Yeah.
So there's your context.
So I think the answer is no. We don't do any kind of sensor fusion or multisensory extraction. I would say that there's opportunities for us to use MMG or microphones to look at vibrational things, et cetera, but all of that is still dependent on an actual movement. What I'm pretty much obsessed with, and my co-founder and the science team is obsessed with, is breaking through the restrictions of movement. So getting more information about movement is sort of not the point for us. Now, when you're doing diagnostic work, I think the game kind of changes because you're basically trying to say, like, and especially if you're doing ML, the intersection of ML and diagnostic work, you want as many different kind of views of the same data, ultimately the same data source as possible, because nothing is high enough fidelity. But I'd say with respect to the nervous system, what else is there other than the spiking activity of neurons? There are people out there, theoreticians, who can talk about, the nervous system does more than just generate action potentials. I'm not in that theoretical religious community. I am in the community that says, the irreducible atomic level of information in the nervous system is an action potential. And if I can get action potentials at scale, there's nothing else to see beyond that. So that's sort of our somewhat religious point of view.
And just, you think you're happy with the way you're getting it out? Do you have a wish list of ways you could get information about the action potentials out better?
I would love to get to, for instance, let's estimate 15,000, maybe 20,000 that control all of the movements here. I would love to get all 20,000 instead of a subsample of a couple hundred. I would like to do it in a way that, doesn't require me to wear something firmly on my skin. I would like to do it with for instance, much, much higher density of electrodes and a totally different synthesis of electrodes, rather than metallurgy, silicon probes, et cetera, and think of 1,000 probes instead of 16 probes. But all of that is about still getting better access to that electrical signal that I'm looking for, as opposed to, a proxy signal, where MMG or some vibrational information would be a proxy for muscle movement. That's a deeper technical
Next question, real quickly. Who's got one over here? There's one right here, and then we'll go in the back, and then we're done.
So how do you deal with noise from the neuron, and do you denoise the signal, or how clear is that signal that you're reading from the skin?
Oh, I want to answer that question, but I can't. I think we're treading too close to a very active IP of ours. What I can tell you is we can sort a lot of individual neurons out, and we can retrieve every spike from the ones that we sort. But I can't really go into the signal processing techniques right now.
Cool. Thank you.
I like questions that digging in
Look for
very
our
close. One in the back. Somebody raise their hand way in the back. And then we'll hurry up and get one more. Somebody over there. Sure.
Hi, my name is Jasmine. I go to Comp Sci High.
Cool.
You know how you said that you're 19, that when you started doing technology? How can you tell the teenagers to not stop trying?
I love that question.
Boy, for me, it's weird. The reason I didn't go to college is because I was poor. I was a bright kid, but I was poor. I left high school when I was 15 and didn't go to college. And the reason I started writing code, especially full time, is because I had to eat. And I just made sure that the work I did to eat lined up with what I thought would be something a bit more interesting. So,
that means I gave up a big part of my youth. I didn't go to college. I didn't get to have that experience that everybody else gets to have in their early 20s. The trade is, I got to make some money earlier and get a bit more self-determining in my life later. But it was getting my, how I got to eat lined up with something I actually cared about doing. And sometimes that just requires holding your breath. But the number one thing I'd say is do what I did when I was 12. Find really fun, interesting people to play with.
That's great advice. One last question in the back. There you go.
Sure. I'm a superintendent of schools in a public school system in New Jersey. So thank you for your presentation today. Intrigued by your work studying the classics, stepping completely away from the technology, enabling you to step back into the technology. A lot of people in this room probably have been focused on technology for a long time. Can you speak for a second about the lessons you took out of that process? Thank you.
I spoke at Columbia several years ago, and I opened with this line from Seneca. I won't give you it in Latin, I'll just give it to you in English, which is, what matters most is not what matters most is distinguishing between avoiding your death versus extending your life. And that, the repercussion of that is, are you investing in a life that you want to be living rather than just spending your time in a way that is foregoing death, just taking up oxygen. I don't know, I think that line has always had a profound impact to me from the first time I read it. And I'm not sure what else I can say other than Greek and Latin are fun to read, and it's a little bit stunning how much nothing has changed in 2,000 years.
I don't want this to end. There was one more question. Oh, right here, in the back, way in the back. She was waving her hand way in the back. Go. We'll do that in the last question. We got you here, Thomas. We got to get a couple more questions out of you.
Yeah, I'll go all day.
I would too, but we got a lot of great other people we got to bring up.
Hi. Thank you for your talk. It was really amazing, your work. I'm a LDV Vision Summit volunteer, and I have a question about assistive technology. What do you think is the future for computer vision and helping students with special needs or anybody who needs assistance of that nature?
Oh boy, I have not thought about that. And in particular, not as it intersects with CV. What I like about what we're doing, to make it self-directed here, is that we're creating technology that doesn't really care a lot about whether or not you have a bunch of motor disorders. We have, my co-founder actually has an essential tremor in his right arm, and one of the weird things of this is it makes a mouse difficult to use. But the mouse he uses via this kind of filters out that tremor and just gets to the intention underlying the moving the cursor thing. So he gets a better mouse. But I didn't design it. He didn't design it that way. That's just a result of the technology. You build a technology for 8 billion people, and what you find out is you actually are able to include a bunch of new people that might have gotten left behind by an old mechanical technology. To go for I don't know how to answer your question because that's such a huge question. I would say stay around for Jeremiah's talk and see what he's going to do to help people in the assistive community, because it's pretty extraordinary.
Cool. Okay, 2 last questions from me, and then we're going to head out. In a one-sentence answer, advice for the very technical people that want to commercialize and build a business.
Get partners.
Okay.
Before starting.
Great. So get partners before starting. And now there's another.
I mean co-founders.
Yeah, co-founders. And now there's another one. As people, you said, are the most important thing. What I like to kind of end with is in one-word answers. Your favorite personality trait of those you like to work with, and your least favorite personality trait.
That's easy. My favorite personality trait is curiosity, and my least favorite is what I call smartest guy in the room. People who are trying to demonstrate their intellectual superiority.
Thomas, thank you very much. A round of applause. That was fantastic. Thank you very much.
Thanks.